Hello, ladies and gentlemen. My name is Fang Zheng. I'm from the Institute of Information Engineering, Chinese Academy of Science, Beijing, China. I'm very honored and proud to have the opportunity to speak at this meeting. Today, I would like to present my paper, High-Quality Candidate Generation and Sequential Graph Attention Network for Anti-Linking. Last, I will give this talk in 4 parts. The first part introduces anti-linking. Then is our work and experiments. The last is the conclusion. So, what is anti-linking? Anti-linking is the task of mapping mentions in text to corresponding entities in a given knowledge base. This task is a fundamental part in the field of natural language processing. For example, there are 5 ambiguous mentions in the text, and each mention has some candidate entities in knowledge base. Here, Curry may refer to Stephen Curry or Dale Curry. Our anti-linking system needs to align mention Curry to real target entity Stephen Curry. Now that we know what anti-linking is, then how do we solve this problem? Anti-linking tasks usually consist of 3 stages: mention detection, candidate generation, and anti-disambiguation. Because mention detection is usually studied as an independent task, we focus on the last 2 stages. For the candidate generation stage, name dictionary-based technicals are the main approach to generate candidate entities. According to our survey, existing publicly available candidate sets are all constructed through static dictionary, Yago, and CrossWiki. The former dictionary is built from entities in Yago knowledge base, while the latter established a general mapping from strings to Wikipedia entities. However, restricted by dictionary size and construction time, many long-tailed and newly generated entities cannot be recalled effectively. To extend the semantic of mention, some anti-linking systems try to retrieve candidate entities by using web search engines. Someone generates candidates by searching sentences from Wikipedia articles and directly using the human annotated entities as the candidates. But for some entities that have low specific meanings, such as country common entity, it's difficult to recall them by sentence matching. Others submit mentions together with its local context to the Google search engine and identify entities whose Wikipedia pages appear in the top results. In fact, they already use Google's anti-disambiguation service when recalling candidates, which makes it difficult to evaluate the real performance of the anti-disambiguation model. For the anti-disambiguation stage, there are 2 main models. The one is graph model, the other is sequential model. Graph model usually build an anti-graph based on knowledge base to capture coherent entities for all identified mentions in a document. Most of them calculate the pairwise scores between all candidate entities and select the most relevant group of entities as the final result. Sequential model rank mentions based on their ambiguity degree and deal with them in a sequence manner. However, these sequential models can only observe previously referred entities without considering the subsequent ones, which may also provide useful clues for disambiguation. Here, we give an example to illustrate these problems, as shown in figure. When we disambiguate Curry, except from previous referred entity Golden State Warriors and National Basketball Association, the subsequent candidates Klay Thompson, Golden State Warriors can also provide useful information. Graph models can utilize the information of subsequent candidates, but they also add a large number of long-target candidates, like list of Golden State Warriors seasons and National Banking Association entities, which may introduce noise when performing collective disambiguation. So, how to combine the advantages of graph and sequence models to make full use of the topic coherence and reduce noise interference is the problem that needs to be solved. To address about two issues, we propose our own solution. In the candidate generation stage, to improve the gold recall and the quality of candidate set, we retrieve candidate entities from three aspects. The first is retrieving candidates with a thinner surface form of the mentions, such as the mentions, abbreviations, alias name, full name, and other variants by utilizing online dictionary and Wikipedia search engine. The second is retrieving semantic relevant candidates by expanding the queries with the mentions, context keywords, or other relevant mentions. The last is recalling candidates using Google search engine when above two mechanisms don't work well. In the entity disambiguation stage, our model dynamically changes the input loads and relations according to the carrying states for each mention, except for its own candidates. The previously referred entities and the subsequent mentioned candidates are also encoded by a graph model. In this way, our model not only utilizes more related entities but also reduce the noise information. Besides, in order to pay more attention to the previous and subsequent target entities, we use the attention mechanism to assign different importance to different adjacent nodes. Our anti-disambiguation system mainly includes three modules: local encoder with BERT, global encoder with sequential graph attention network, anti-selector with multiple information. The local encoder uses BERT to encode mention context and entity description. In the global encoder, the global interdependence between mentions will be captured by a graph attention network. In the anti-selector, some lexical and statistical evidence will be combined with local and global representations to select the target entity. In the following, I will introduce technical details of these modules. In the local encoder, we use the complete sentence in which mention is located at the context. As for the candidate entities, we select summary keywords in corresponding Wikipedia pages as their description. Then, the mention context and entity description are packed together into a single sequence. After fine-tuning the BERT, we obtain the mention context vector and entity description vector. We are average pulling over the hidden states of the corresponding tokens in the last BERT layer. In the global encoder, candidate entities are input in a fixed order. We first rank mentions based on the value features and the semantic representations. Based on statistical and textual features, we train a XGBoost model to rank candidates. Moreover, BERT distinguishes candidates based on semantic information. Combining results of the BERT and XGBoost model, we rank mentions in text. After sorting mentions, we encode their candidate entities in a sequential way. According to the position of current mention, the sequence is divided into two parts: mentions that have been disambiguated and mentions that have not been disambiguated. The loads in our graph include three types: the previous referred entity load, carrying the candidate entity load, and the subsequent mentions candidate entity load. At the same time, we define three types of edges between pairs of loads: an edge between previously referred entity load and carrying candidate entity, an edge between subsequent mentioned candidate and carrying candidate entity, and a self-connection. After building sequential graph network, we use the graph attention network model to generate the global representation for each entity. Graph attention network is a convolution-style neural networks that operate on graph-structured data, leveraging masked self-attention layers. With the help of graph attention layer, We can assign different importance to different adjacent nodes and capture the relevance between the target candidates. Aiming at combining the local and the global information, we propose an anti-selector to collectively disambiguate mentions. For each mention and its candidate entity, we generate the input vector as follows: the local mention context vector, entity description vector, global representation output by graph attention network, and lexical and statistical features. Then, we fit the calculated vectors into a multi-layer perception and use a margin-based objective to fit parameters. In order to evaluate the effectiveness of our candidate generation and entity disambiguation method, we conducted a series of comparative experiments. We first analyzed the quality of our candidate entities and compare them with previous systems. Generally, a good candidate set should have high gold recall and strong correlation between mention and candidate entities. For gold recall, we can see that our module achieved best performance on all four datasets. To evaluate the correlation between mention and candidates, we calculate the text and semantic similarities between them. The results show that our candidate entities are more relevant to corresponding mentions. Moreover, with the number of candidates close to us, the average page view of previous candidate set is only half that of ours. This means that many popular mention-related entities have not been recalled by parallel systems. In our system, the candidate sets are built from three aspects, which are the surface form of mention, the semantic extension, and the exception handling. To investigate the contribution of each part, we calculate the corresponding gold recall and show the statistical results in figure. We can observe that mention-based method can recall about 90% of the gold entities in most datasets, and 50% of gold entities can be retrieved by the adding local and global information. To evaluate the effectiveness of our entity disambiguation model, we choose a series of global anti-linking systems which report state-of-art results and gerbil platform. From table, we can see that our model has achieved relatively good performance on AI datasets and ACE 2004 RSS 500. Moreover, we also achieved the best overall performance. To analyze the performance of different modules and investigate their impact on final results, we evaluate the effect of local encoder and global encoder. Comparative results in table show that our model obtains about 3% F1 improvement by using the BERT encoder, which indicates that our model can capture more valuable information between mention and entity. Besides, we found that even with a powerful pre-trained language model like BERT, the F1 is just around 60% if we only utilize local semantic information. Therefore, we combine local information, value features, and global information in the entity selector. To better evaluate the contribution of different modules to the overall performance, we conduct the ablation studies. From the results shown in table, we can observe that BERT is the last three components that contribute about 2% gain of F1. And removing sequential graph attention network decreases the performance by about 3%, and the manufacturers contribute much to the overall performance. This is our all experiment results. Finally, I would like to make a conclusion with this presentation. Firstly, we propose a high-quality candidate generation method and propose metrics to evaluate the candidate sets. Secondly, we propose a sequential graph attention network, which combine the advantages of graph models and sequence ones. Specifically, we utilize BERT to extract local features and introduce sequential graph attention network to capture the topical coherence of mentions. In the future, we plan to construct an end-to-end model, which simultaneously optimize candidate generation and anti-disambiguation. Thanks for your attention. If you have any question and advice, please feel free to contact me.